Okay. Okay. So let's start. Wait a minute. Okay. Okay. Good. Okay. So let's continue on the unsupervised learning. Okay. The introduction to the unsupervised learning. Okay. So previously we said unsupervised learning, right? There are some subcategories of unsupervised learning, okay, including the clustering, the embedding, the density estimation, and also finding good explanations of the data, okay. So so basically for the last one, okay, finding the good explanation of data, I think this is actually quite popular nowadays because it directly links to generative models. Okay, and later on we will give you the brief introduction on the basic idea behind the clustering, the embedding, and also the density estimation. Okay, so let me check a little bit. Yeah, okay, good. Here. Okay, so yeah, so maybe I think before I really go into the last category, the brief introduction behind the last category, let's try to first talk about the first three, right? The clustering is basically trying to group. Okay, so trying to group your data set into some clusters, okay, or into some groups, okay, some small groups. Okay, so the basic idea is that we try to perform, or we try to we try to group those similar data points into the same cluster, such that we are able to see how your data set is formed, right? So for example, how many clusters can be used to form your data set, okay, and which data points they are actually close to each other, and which data set they are actually far away from each other, and they are belonging to different clusters and so on. Okay, the embedding basically can be told by this simple example. Here. Okay, so for instance, originally you have a three-dimensional data set. And those dots are your data points. Right? Okay. So although these kind of data looks a little bit complicated, okay, it's a little bit hard to tell what is the properties behind such data set. But sometimes you can try to use the embedding techniques. For example, I can try to project these data set. I can try to project these data set from high dimensional space, for example, 3-dimensional space, to a lower dimensional space, to a low dimensional space, for example, here 2D. Okay, so in this case, when I try to project it, you can use some specific way of projection. We will introduce you those algorithms later on, but you can try to use a specific way of projecting your data set into a lower dimensional space. For example, here in this case, we can try to flatten it, right? Just like try to flatten it. And when you try to flatten it, you can see here, actually, this data set, it might be able to, well described by a two-dimensional, in the two-dimensional space. Okay, so basically this is trying to find out the embedding, okay, the embedding of your data set. So you can think it's similar to a procedure of projecting your data set from higher dimensional space into a lower dimensional space, but you try to keep some properties of your data set doing such projection. Okay, and the third category is the density estimation. So basically, the density estimation is trying to find a function. It's trying to find a function of your data set such that, so for example, your data set is X, is a capital X. Okay, so you try to find a function F such that the F of your X, the F of your data set can well approximate the probability density of your data set P of X. Okay, so for example here, for example here you have a 1D data set. Okay, and your 1D data set, and the data points in your 1D data set are annotated by those curves, red curves. Okay, and actually you can try to by using the technique we have mentioned previously, the Poisson density estimation technique, right? I can simply put a Gaussian. I can put a small Gaussian on every data point. I can put a small Gaussian on every data point, and in the end, I try to sum up all those small Gaussians, and I end up with this curve, curve in black color, and this is a good density estimation of your 1D data set. Okay, so it basically provides you a function, okay, a function that can well approximate the probability density of your data set. Okay, and this is unsupervised learning basically, right? So no matter for clustering, embedding, and density estimation, they all belongs to the category. They all belongs to the unsupervised learning, because you actually don't have any labels of your data points, right? Okay, and the fourth category, okay, finding good explanations of your data, okay, so it's basically linked to generative model. So first I will talk about generative model, and then I will give you a just very high level idea about this category, this subcategory, okay? So so previously we said, okay, there are three main categories in machine learning, right? Supervised learning, unsupervised learning, and also the reinforced learning, right? But within these three categories of machine learning, actually the reinforced learning is a little bit specific. It's a little bit specific or spatial. Okay, and actually for the supervised learning and unsupervised learning, right? They are their concepts are very easy. Their concepts are very easy to understand, right? The supervised learning is trying to find a mapping between your input X and your Y, and you are provided the training data. The training data you are provided the training data composed of the input and output pairs, right? And basically you're trying to find a mapping from the input to output, right? And for unsupervised learning, basically you only have the input data. You only have a lot of data points, right? And you try to find out some patterns or try to find out some properties from these data points, but you don't have any corresponding labels. Okay, and actually the supervised learning and unsupervised learning, they are closely related to the discriminative model and also the generative models, respectively. Okay, so what is the discriminative model? Okay, so the discriminative model is actually related to most of the machine learning models you have learned so far. For example, like the SVM, the SVM, those classifiers, right? Those regressors, most of the time they are belonging to the discriminative models, because, for example, a typical example comes from the classification, right? The classification that, for example, you want to estimate, or you want to predict the class of an input data, right? So for example here, okay, you have an input data X, and then you want to predict, how likely these data points, these input data X belongs to a certain category. Okay. Okay. So for example here, right, you have two groups of data. One is the images of sunflower, and another one is the images of bananas, right? And then you want to learn a decision boundary for example, in a feature space, right? And then in that feature space, you try to separate these two groups from each other, right? And during the prediction time, right, you given a test image, then you first put this image into the feature space, and then according to this decision boundary that you learned during the training, right? And then you want to classify this test image into the banana or sunflower, right? So actually, such procedure, right, is in the prediction. Such procedure, right, is trying to model the posterior, right? Because given the data X, given your observation, I want to predict what is the class, okay, Z. Okay, so this discriminative model, right, is trying to, its basic idea is trying to model the posterior probability, right? So once you have similar equations like in this form, right, for example, like given an input, how likely its class is sunflower or banana, if you have some similar equations related to this form, then most of the time we try to solve it from the discriminative methods, right? We try to discriminate between different classes or different categories and so on, right? Okay, so this is trying to model the posterior probabilities in the discriminative model, right? And how about generative model? Okay, the generative model is actually it's actually from another perspective. It's trying to see the whole problem from another perspective, right? If you guys are familiar with the Bayesian story, okay, the Bayes, okay, the Bayes theorem, right? You know that actually the posterior is proportional. The posterior is proportional to the product of the likelihood and the prior, right? So for example, here we say in the discriminative model is trying to take care of the posterior, right? Given the Z given X, P of Z given X. And in the generative model, right, we are trying to take care of the product between the likelihood and the prior, okay? And actually they are proportional to each other, right? According to the Bayes theorem, okay? The likelihood is P of X given Z. And the prior here we can take it as the P of Z, right? The P of Z. So, okay, so for instance, in this example, okay, let's say the Z is related to a human pose, okay, the human pose, okay, and the X is related to your image, right? And I can first assume that the human pose can be described by the configuration of my body joint, right? So for example, I can say, okay, maybe I have a joint on my shoulder, and for such joint, it only have a certain range of movements, right? And I have another joint in my elbow, and also I can provide a reasonable moving reasonable range of the moving angles for my joints, for my elbow joint, right? Okay, so we can try to use the configurations of different joints, and for different joints they have their own possible moving angles, right? And those possible moving angles actually is they can be assigned according to your prior knowledge about the human body, right? Okay, so for example, I have some prior understanding about the human body, right? And I know actually the shoulder joint, the elbow joint, or the ankle joint, they have their own specific range of the rotation, let's say. Okay, so I have this prior knowledge, so I try to put it in my prior. So there's a prior here trying to model the knowledge you already have about for example, the human pose, right? So we have the P of Z. Okay, the P of Z, right? And then what is the likelihood? The likelihood is that, okay, now suppose I have a I have a guess. Okay, I have a guess of the human pose. Okay, I have a guess of human. So for example, here I guess maybe this I guess that the human now is with this pose, right? Running and with the hands up, Okay, but given such a pose, right? Given such pose, how likely the observation, the image observation follows your guess of the pose, of the human pose, right? So this is a likelihood, right? So given a pose, how well it's it fits the body of the human body in this image, right? Okay. So basically, first you know how human pose can be, right? And then you have the likelihood that okay, given a pose, how well it fits your observation. Okay. So this is a generative model, right? It's trying to it's trying to it's trying to use the likelihood and the prior, okay, to take care of your problem. Okay. So basically, if you take a look of the meaning behind the likelihood and prior, right? Okay, is it can be understood. It can be understood from another perspective. It can be understood from another perspective. Okay, this is the way that I personally prefer, right? So actually, the generative model it models the likelihood with the prior, right? And it's actually can be understood by this sentence, right? Given some data, okay, given some data X, okay, I would like to train a model to generate sample like the given data, okay? So for example, in other words, okay, you are having a data set, right? And now I want to learn a model, and by using this model, I'm able to generate a lot of samples, and ideally, those samples should be similar to the given data set. Okay, so here comes an example. For example, the data set you are having now is the data set that you are having now is a bunch of images of dogs, a bunch of images of dogs. Okay, a lot of images of dogs, right? And now what is PZ, right? The prior understanding can be, for example, like the some attributes related to the dog, right? Okay, some attribute related to a dog. For example, the color of the dog, the species of the dog, if it is a Chihuahua or if it is a a corgi, right? So you have some prior understanding about the dog, right? I know the dog can be categorized into some species, and also we can tell different dogs, they might have different colors, they might have different hair length, right? Our human beings, we already have some prior knowledge about the dog according to attributes, right? So now this PZ is trying to take care of the prior knowledge that you already have for dogs, right? Okay, so so those attributes those factors in our prior knowledge we also name them as the latent variables. Okay, and how about the likelihood? The likelihood is like that. Okay, given Z, I would like to see how well is my data can fit it, right? Okay, so given the Z, right, and here the Z is related to the attribute of the dog, right? So now, given a starting of the attribute, for example, if I provide you a description, if I provide you a certain description that, okay, try to imagine a dog. Try to imagine a dog that this dog is a Chihuahua. Its color is black color, and its hair length is pretty short, and how fat it is, how tall it is, right? If I give you this kind of I give you this kind of description of the attributes of the dog, then you are able to somehow imagine. How the dog will look like. Okay, so that is related to the likelihood, because given a setting of the attribute, then you are able to imagine the image. You are able to imagine the image of such dog, right? Okay, so now if now I try to have samples, I try to have samples from my prior knowledge, right? I can sample a lot. I can sample out a lot of description, right? I can sample out the Chihuahua, black color, and sample out the Corgi, white color, and so on. I can sample out a lot of different descriptions, right? And for each of the description, I can imagine, okay, I can imagine how the dog will look like, right? So this procedure is similar to generate the images of the dog, right? Okay, I can sample a Z, and given a certain Z, I can try to imagine what is the corresponding image, right? So this is a generation of your data, okay? So based on these generative procedure, or we say the process of the data formation, I can generate a lot of samples. Right? But maybe in the beginning of your training, generative model, right? Maybe your model is not that good. Your generative model is not good enough. Then you might generate some images like this. They look like dogs, but maybe it's like a toast. It's just like hot dog, right? They are not that similar to the data you are given, right? So now we can try to say, okay, maybe your sample, the data distribution of your samples is not able to well approximate the data distribution which is given to you, right? Then you need to update your model. Such that your generative model, after the update, it can be generating the samples which are more similar to the given training data set. Okay. So basically, the generative model is take care of the likelihood and prior, and basically the idea behind the likelihood and prior is exactly a process of the data formation. Okay. So if you are trying to learn the generative model, basically what you are trying to do is that, given the training data, you try to train a model that is able to generate some samples which are similar to the given data set. Okay, to the given data set. So this is a generative model, right? Okay, but why do we need such generative models, right? I would like to quote from the Richard Feynman that what I cannot create, I do not understand, right? So try to imagine that if you are able to create something, for example, if you want to make up an animation, or with a cartoon, right? Then you need to have full understanding about the characters, right? So for example, I need to have the full model of each character in this animation, such that I can create this animation, right? Okay. So if you are not able to fully, create what you want, maybe you do not have the full understanding yet. Okay. So the generative model is trying to learn the generative procedure. Is trying to learn the generative procedure of your data set. Okay, And based on such generative procedure, you try to have the full understanding of your data. Okay, and it will be actually quite powerful. Okay, so later on, I think maybe in the last part of this session, we will talk about some models that some models that are belonging to this subcategory, and then you can see how they are used. Okay. Okay, so now we will go back to the first category. We'll go back to the first category, the subcategory in the unsupervised learning. It is the clustering. It is the clustering. Okay, so the clustering its basic goal is trying to partition. Okay, your data set V. Okay, try to partition your data set V such that, or you can use another way of saying, you try to group your data set V into some small groups, right? Such that the data points, or the elements in the same subset or in the same cluster, they are similar to each other, but the elements in different subsets, they are dissimilar to each other, right? Okay. So for instance, given this image, all the pixels in this image can be treated as a single data point, right? And for each data point, or we say for each pixel, they have their own intensity values, right? And then we can try to group those data points or those pixels according to their intensity values. So basically, we can try to group the pixels with similar intensity values together, and the pixels with different with quite different intensity values into different groups, right? And after clustering, after such clustering, then I can obtain, for example, this result, right? The pixels now colored by the red color, those pixels, okay, they belong to one group. Another portion of the data points, they are grouped into the red, into the blue color, and also the green color. Okay, so now you can see here, by using this clustering, now I can partition my image into three regions, into three main groups. And you can see here the red group is mainly about human, the blue group is mainly about the sky, and the green group is mainly about the grass. Okay, so by using the clustering, even if it's unsupervised, then I can try to partition my data. I should try to partition my data into some groups, and each groups, they might have their own semantic. They might have their own meaning, or like, for example, the semantic of the human, the semantic of the sky, and the semantic of the grass. Okay. Okay, and I hope you, I hope you can really, think of something, right? Okay. Basically here, as we just mentioned, right? The elements in the same cluster, they are similar to each other, but the elements belonging to different clusters, they are dissimilar to each other, right? So there's a very important there's a very important thing that you need to define first, is the similarity, right? So you need to first define the similarity, then you perform for you to perform the clustering, right? And if you think of the similarity, right? If you're now trying to use the inner product as your similarity measure in the feature space, and I hope you can still remember this is related to kernel, right? Okay, so basically clustering is an optimization problem, right? Because for a data set, it can be partitioned it can be partitioned by different ways. Okay. For example, maybe I can partition it according to, for example, according to the intensity color, intensity value, or I can cluster those. Sorry, given this image, right, I can cluster those pixels according to the intensity value, or I can cluster them according to their spatial location, or I can cluster them according to other features, right? So you might have a feasible set of the partitions. Okay, you might have many different ways of partition. Okay, of your data set, right? So how you are going to separate, or how you are going to apply the clustering is all depends on the application. Okay, it all depends on the applications. And basically, if you have no understanding about your application and you directly use a randomly chosen clustering method, and it might cost you 10. Okay. So for unsupervised learning, most of the time you need to have a good understanding about your problem first. Then you choose the proper tool, proper clustering tool, or proper embedding tool, or other tools in order to deal with your data set. Okay, so the most important thing is that you need to first have a good understanding about your data set and about your application. Okay, so and here I would just want to just provide you such information that most frequent and open questions in the clustering area is that how do you decide the number of clusters, right? So now if I want to group my data set into some subset, then most of the time for most of the algorithms, you need to first decide how many clusters you want to have. Okay, how many clusters you want to have. So the way that you use to make such decision, okay, will be different across different algorithms. Okay. So that's now going to introducing different clustering algorithms. Okay, the most popular clustering algorithm is a k-mean. Okay, so its objective can be described this way, right? Assuming now I try to cluster my data points into k clusters, right? And then for each cluster, I can compute the center of this cluster. The center of this cluster, you can think this just like the average of the data points belonging to the same cluster, right? If I simply average them, I can get a center, right? So the center of each cluster, okay, the cluster now is each cluster is now denoted by Ci, okay, and the center of this Ci cluster, we use a variable mu I to represent it. Okay, then the objective function of the k-means is trying to minimize. Okay, the Euclidean distance from the data point to its corresponding center, right? So for example, if now I know a data point xj, it is belonging to a specific cluster Ci, then its distance with respect to the mu I should be minimized. Okay, and then I try to sum up all the distance from the data points to their corresponding cluster centers. Okay, and I try to perform the minimization on it in order to find out my clusters Ci to Ck. Okay, and so basically in this problem, okay, what you are trying to do is actually, okay, finding an assignment of the data points to the cluster, right? I need to have assignment. Okay, how to assign these data points xj to a specific cluster ci. Okay. Okay, so I need to find an assignment from the data points to the cluster. Okay, as well as a set of vectors mu k, that is the center of each cluster, right? So now I want to find out these two things. Right? The assignment from the data points to the cluster, and also the center of the cluster. Okay, okay, and the assignment and the assignment of the data point as well as the center of the clusters should be able to minimize this objective function. Okay, should be able to minimize this objective function. And I believe you guys have learned something, okay, on such a clustering algorithm, okay, in the first half part of this machine learning machine learning course, sorry. Okay. Okay. So we can actually try to reformulate the objective function. Okay. So basically, here you can see we have this summation. Let's say the xi if it's within the class ci. Okay. So actually it can be reformulated by using a assignment vector, or you can another way of saying is the indicator variable, right? R and K, okay, is equals to 1 if a data point xn is assigned to the k's cluster, right? Then the corresponding R and K equals to 1, otherwise equal to 0, right? So your objective function can be now rewritten in this way, okay? And of course, we know that R and K, for the value of this indicator variable, it will be either 0 or 1, right? Okay? So your objective function now can be rewritten this way, and we name it as a distortion measure, okay? So to find out a solution, for this distortion measure, to find a solution of the assignment, which is the R and K, and also the cluster mean mu K. Okay, to minimize such distortion measure. Okay, here comes the main algorithm behind the k-means. The main learning procedure of the k-means. Okay. So for the k-means clustering, right, you can first initialize the centers mu k, right? So for example, you can randomly pick k data points as the initial gaze, your initial gaze of the centers. Then you do the following two steps iteratively until it converge. Okay. The first step is the E step. It's trying to classify all samples according to the closed list mu k. So basically, it's trying to keep the mu k fixed, try to keep the center of the clusters fixed, and then trying to find out the assignment, that is able to minimize the distortion measurement. Okay, so basically you're trying to fix the mu k and find the R and K, right? And another step is trying to keep the R and K fixed, right? I already know that the assignment of each data point to their corresponding clusters. Then I try to re-estimate or recompute the mean, the center of each cluster, right? So in this step, you're trying to keep the assignment, or we say the indicator variable R and K fixed, and try to minimize the distortion measure with respect to the mu k. Okay, and you try to do these two steps iteratively until there is no change in the mu k. Okay. Okay. So why we say this is E step and why we say this is M step, because the whole algorithm is related to the exploitation minimization. Okay, so the E here is the exploitation and M here is the maximization. It's a maximization. Okay, so this is the EM algorithm, the exploitation maximization algorithm. Okay, is widely used when you need to estimate when you need to estimate the values of multiple variables, right? And the basic intuition behind that I try to keep a subset of variables fixed and estimate the others, and then I iteratively fix a portion of variables and estimate the rest. Okay. Okay, so the k-means itself is a combinatorial optimization problem. Okay, the combinatorial optimization problem is a topic that consists of finding an optimal objective from a finite set of objectives. Finding an optimal solution from a finite set of the possible solution. Okay, because we're trying to find out what kind of combination, right? The combination here in the k-means is the combination of the data points into the cluster, right? I'm trying to find out a combination that is able to minimize a certain objective function. Okay. So the k-means itself is a very simple iterative algorithm. It can converges pretty fast, but it only finds the local minimum, right? Okay, so actually the solution of your k-means algorithm will largely depend on the initialization. So once you have different initializations, you might end up with different results of the k-means clustering, right? Okay, and here I just want to give you the why you have these two, why you will end up with these two steps in the k-means, right? Okay, so as I said, in k-means there are two variables you need to estimate for. One is the RNK, the indicator variable, or we say the cluster assignment. Another one is the mu k, right? The center mean, the cluster, okay, the cluster centers, right? So, and this is your objective function. Okay, this J is your objective function, right? Okay, so if you try to compute the optimal solution with respect to the RNK when keeping the mu k fixed, right? Then actually the optimal solution for RNK can be written in this way. Okay, because J is just a linear function of RNK. Then we can optimize for each n separately, right? So RNK will equal to 1 if k is the argmin of this Euclidean distance, right, and 0 otherwise. Okay, so this is what you use in the E step. Okay, and then in another step, right? Because previously in the E step we try to estimate for the RNK. Okay, and in the next step we should try to keep the RNK fixed and estimate for or optimize for mu k, right? So given this objective function, okay, this distortion measure, I try to compute its partial derivative with respect to the mu k, okay, and make it equal to 0 in order to find out the optimal solution of the mu k. Okay, and you can do the math on your own. You will find out actually the mu k can be written in this analytic form, right? And if you see such analytic form, okay, it is exactly trying to compute the center of each cluster, right? Okay, so that is why you try to iterate over at least 2 steps, right? One step is to keep the mu k fixed and optimize for RNK. Another step is to keep RNK fixed and optimize for the mu k. Okay, So you try to do these two steps iteratively, okay? And because this is similar, these two steps basically follow the idea of the EM algorithm, and we know the main problem of the EM algorithm is that most of the time it can only give you the local minimum, right? The local solution, okay? Okay, and I hope these steps can also remind you the Gaussian mixture model, GMM. And here, and aggressively, we have K Gaussians in GMM, but all these Gaussians are isotropic, right? Because here, right, we only try to minimize the distance to from the data point to the center, right? So given the center, right, given a center, and this center can be treated as a mean of a Gaussian, and actually I expect all the data points are, within a certain distance from, their distance with respect to the corresponding centers can be minimal. So actually this Gaussian is basically follows a isotropic Gaussian, okay? Okay, so here I just want to show you that different, here comes different results of the k-means clustering on the same data set. Okay, you see different results because actually they are using different initialization. They are using different initialization. So different initializations can lead to different clustering results. Okay. Okay. So the potential problems of the k-means clustering is suboptimality, right? Because it converges to only local minimum, which depends on initialization. Okay, and also you need to choose the metric, right? Previously, we simply say, okay, you can use the L2 distance, but of course, you can use different kind of distance, or you can use you can first project your data into different feature spaces, right? So you need to choose the metric with the similarity, right? And the third problem is that you need to choose K, right? I need to choose, so as you can see from such algorithm, right? You need to first initialize the centers mu K. So when you initialize the centers mu K, that means you need to first decide how many clusters you want to have in the end. Okay, so you need to choose the number of clusters K. Okay, and sometimes the problem is more complicated. Okay, when k-means only can detect the clusters that are roughly linearly separable, right? So for example, you are given such 2D data sets. You are given such 2D data sets. If I directly perform k-means on this data space, then this would be the possible result that I will have, right? So you can see here, this kind of clustering result may not be good for us, right? Because for our human being, if we are given such data sets, right, we can easily say, the inner circle is one cluster and the outer circle is another cluster, right? But if you directly apply k-means on such data set in the data space, then very likely you cannot get the satisfactory results. Okay, so how to deal with this? Okay, the way to deal with this is actually simple, right? Still remember our feature story, right? We can now first project. Okay, given such data set, okay, we know that if we directly apply k-means on the data space, it might be not that good. But if I first project my data set into a feature space, then maybe on less higher dimensional feature space, I can apply k-means and it can give me good separation between the data points. Okay. So I hope it can still remind you the important idea about kernel, right? So let's say we first project our data point into a feature space phi, right? And then in that feature space, okay, we now assume now our indicator variable is this alpha kn, okay, alpha kn. So alpha kn equal to 1 if the data point xn is assigned to the case cluster. So it's just similar to it's just the same as Rnk we have previously, right? But here we use another variable alpha kn to represent the indicator variable. Okay, so the center of each cluster can be computed by this formula, right? This is quite simple, right? At first, if alpha kn equals to 1, then actually this phi of xn is considered into computing the center, okay? Because that means this xn is now assigned to the k cluster, okay? So mu k in the feature space now can be written in this way, okay? And the Euclidean distance, right? The Euclidean distance in the feature space, okay? Or this is the original objective function, the distortion measure, right? But now if we turn it into the feature space, then the mu should be in the feature space, and also the fj should be also in the feature space, right? So the Euclidean distance between a certain data point to its corresponding cluster center in the feature space, okay, can be written in this way. Okay? The phi of xj minus mu k phi, and we have the L2 known. Okay? So if we have mu k phi represented by this form here, okay, and then we expand it, right? Because this is the L2 norm, the Euclidean norm, right? So actually it can be written, it can be expanded and written in this way, okay? So because you will have the phi of xn square, right? So you can actually it's related to the kernel function, okay? The kernel function between xj and xj, and this term, the second term is square is related to this, okay? So you can see here that you have the multiplication between alpha and also the k between different data points, okay? And also you have this term here, and you can see in this formula, everything can be represented by the gram matrix, right? Because everything appears as a product, as a scale product of the x, and that is why we can use the kernel, right? So now this technique is named as the kernel k-mean, okay? It's the kernel k-mean, okay? Okay, let me just give me 1 or 2 more minutes to finish this. Okay, so so basically, now you can simply use the kernel function, right? So as I said, the benefit of using the kernel function is that once you know how to compute kernel, it is fine that you don't. That is fine even you have no idea how to compute a feature, right? Okay, so the basic idea is that, okay, in the original data space, we know maybe it's pretty hard to perform k-means to get the satisfactory result. So we try to use the kernel function. Okay, we try to use the kernel function. That means we first try to project our data points into a high dimensional feature space, then we perform the k-means over there. Okay, and all the computation of the k-means can be now replaced by the kernels, right? But you still use these 2 steps algorithm, right? The n step and e step, okay? To get the solution of the cluster assignment, okay? So one more thing I want to tell you is that you can first apply an initial clustering, okay? You can first try to provide an initial clustering and use these clustering results to reorder your data, right? Okay, and by using the reorder data to compute the gram matrix, okay, and you visualize your gram matrix, then you can see that the block diagonal structure, if the clusters are uniformly dense, which hence provides a good way to estimate the number of clusters. Okay, so the basic idea is that, okay, I can use some random clustering algorithm to perform an initial clustering, right? And now, so for example, I know the x X2, X7, X9, they are belonging to the same cluster, right? So I can put the X2 here, X7 here, X9 here, and for example, X1, X3, X4, X5, X6, X8 here. So I try to reorder. I try to reorder my data according to my initial clustering results, right? Then after reordering my data, I compute the grand matrix. Then I can try to see, right? Ideally, those data points, they are for those data points which are initially grouped into the same cluster, right? They are more similar to each other. And the data points across different initial cluster, they are dissimilar to each other, right? But anyway, when you try to visualize the grand matrix, ideally you can see this kind of like block diagonal structure, right? Because maybe these values here is bigger, and the off diagonal place they are smaller, right? So you can try to see how many blocks you are able to tell from this visualization of the grand matrix, right? Okay, and how many blocks this kind of information can provide you a good way to estimate the number of clusters, okay? Okay, because we say in k-means you need to determine how many clusters you want to have around now, right? So this is a good way for you to roughly tell from the grand matrix visualization, okay, about the possible number of clusters that you want to have. Okay, so we will stop here and then we will continue on introducing the spatial clustering next time. Okay, thank you.